Good evening, everybody. Welcome to Shop Talk, hosted by the Triangle Area SQL Server Users Group. So tonight we have with us what I would say is a great cast and character, excellent dramatis personae, directly over, whoops, that away. I don't even know which way she is anymore. We've got Mala. How you doing, Mala?
Doing well. Good evening.
And I know which way Mike is going. He's any which way but here. How you doing, Mike?
That was a great movie. Doing well, thanks. Hello, everybody.
All right. So the premise of Shop Talk, in case this is your first time, or in case you've had several concussions since the last time we talked, in which case, that probably want to get that treated. But Shop Talk, it's Monday. Hopefully, work is over for you, and have an opportunity to kick back, rewind, unwind, even, and talk a little bit about data platformy stuff. You have questions in chat, drop them in. This is really a chat-driven conversation. We just have some themes and do a lot of talking. So it's talking heads for an hour on topics of the data platform. Speaking of data platform, big announcement, regular announcement that we're doing is the PASS Summit. PASS Data Community Summit is coming up in November, and the discount code, I believe, is still active, Azure 175. So that saves you $175 off of registration for the in-person event. PASS Summit will be in person and online, so it will be a hybrid event this year. It'll be in Seattle, Washington, or wherever you are at the time, depending. Mala also wanted to talk a little bit about precons.
Yes, we have several precons at the summit. I'm just trying to pull up the link as I'm talking. I'm sorry. Yeah, here it is. So all of these things will be presented on Pacific time because the presenters are going to be in person. So the classes are going to be from 8 a.m. to 5 p.m. or 4:30 p.m. I'm not sure Pacific time, but it will be recorded for those of us who cannot, keep up with that time, and available the whole week of the summit. So there are some really good presenters. I'm posting the link right here. If you want to register, now it's a good time. And there aren't as many classes as they were last year. It is less than that, but fairly diverse subjects and good, top-notch presenters. So personally, I'm planning to attend IT6 as I do every year, and I learn more from him. And I probably will attend How to Become a Hybrid Architect by my good friend Ben Weissman and Anthony Innocentino. I think it looks like a great class to go to. That's my personal choices.
All right, so check that out, passdatacommunitysummit.com. So tonight, first topic Mala had was an article that was in SQL Performance by Aaron Bertrand not too long ago, talking about the nature of T-SQL, that it can be very expressive without sacrificing performance. And I do recommend checking out that article. Aaron shows several ways that you can write a given query, and essentially behavior is going to be the same in terms of database performance. He points out that they all essentially use the same execution plan. And in case you're not too familiar with this concept, the idea is that you write T-SQL, that T-SQL gets translated into the code which actually executes. This is what is a hallmark of something called a fourth generation language. So this gives me an opportunity to talk about language generations and the fun of those. So let's talk language generations. This was really my way of immediately knocking myself right off target in terms of going off on a tangent. I derailed myself tonight, but that's okay. It happens sometimes. So generations of languages. We have a 4, which probably means we've got 1 through 3. So let's start with 1. First generation of language, machine language. 1s and 0s. You're writing 1s and 0s, and it's the actual interpretation of those 1s, of those 0s, those ons and offs, the electrical impulses that drive machines. Now,
Is,
machine
assemb-
language.
is that what assembly is, or do you never write that kind of code?
Nope. Assembly comes later. So assembly is not even a first generation language. Literal machine code. So assembly language is the second generation. This was where people simplified the literal machine electrical impulses and turned it into sets of operations on registers. So how am I going to load a piece of information, make it available to the CPU to operate on? How am I going to write a piece of information? How am I going to essentially load, store, move between segments of code? And this all breaks down into machine code. So we can compile it down or translate it down into machine code for the computer itself to run. The assembly language is more for humans than for machines in that respect, relative to the first generation. But anybody who has worked with assembly languages knows that there's a lot of power in them, but there's a lot of, I would say, tediousness. It takes it can take a large amount of code to do a fairly simple task. And therefore, we saw the third generation of languages. Your third generation language is essentially structured programming languages. So we're thinking languages like C, languages, any of the C-friendly languages, Java, C#, anything like Python or Perl or Ruby or Java, you pick it, C++, it's probably a third generation language. If it's a general purpose language that programmers write in order to solve general problems, most likely it is a third generation language. And so the key takeaway from third gen was this is going to be an abstraction on top of assembler and offer up structured programming concepts. We can extend that to include things like object-oriented programming concepts, functional programming concepts. We have more, say, control over the broader picture by giving up some control over the very specifics. So, for example, in C, I don't necessarily care which register you use to accumulate a value. What I care about is that you add 1 to I, because I need to do that in my for loop to move to the next stage of the loop. So that's the way that we're thinking about it. You're moving more and more abstract and less focused on the exactitudes of the task at hand and more on the principle of what we're trying to solve. The fourth generation goes even further than that. Fourth generation starts getting into more declarative concepts. And SQL is, I'd say, the most well-known fourth generation language. A New Hope, there you go. So your third generation language had a 20-minute fight scene that was amazingly was boring. So your fourth generation language, SQL is, like I said, it's the most well-known of them. The idea of a fourth generation language is I don't necessarily care how you solve the problem. Let me explain the problem to you, and you figure out a way to solve the problem. That third gen, second gen, especially first gen, you are solving the problem as the developer. You are saying, in this structure, here is the operation that you will do. You will enter a loop. You will perform this conditional logic. On certain conditions, you will execute this function. You will do this. You will do that. Eventually, I get a result back. That fourth generation, basically, think of a SQL statement as a wish. You know, what I would really like is for some data to come at me from those two tables. And by the way, you can join those two tables together like this. And, you know, I'd like just the data that satisfies this filter condition, this where clause. And I don't really want all of the columns. I really just want this subset of columns. So we're declaring a wish, and the database engine translates that wish into the actual code that runs to read data from files, read data from blocks of memory, combine data together, process data, and restructure it back together in a shape that we can easily handle as humans. The SQL engine is a genie. It is a genie, and sometimes it is very malicious in its compliance. That genie will do what you tell it to do, and sometimes it'll do exactly what you tell it to do, regardless of whether you intended.
Mm-hmm, yeah, very true.
Now, the tricky part is with a fourth generation language, you can be significantly more productive than a third generation language because you are thinking more in terms of abstractions. You are thinking more in terms of desired outcomes than you are in process of how to get there. And so one SQL statement can be the equivalent of quite a few operations in a structured language. For example, if you had to do the equivalent of C, where your memory is, or your data is all stored in binary trees, and you need to combine together information in two binary trees, perform some operations on it, filter it out, and return back a set of results. You can certainly do that, of course. I mean, that's what the SQL engine's doing. It's what the database engine itself does. That's not written in SQL. That's written in C. It's written in C++. Actually, I think at this point it's C++, but don't quote me on that. So you have this translation, this operation that happens to simplify from the standpoint of the user significantly the amount of mental effort necessary to solve a problem. This is where we get to fifth generation languages. So the fifth generation of language is even more abstract, and conceptually a 5GL is essentially telling us, hey, I want to tell you about these facts of the world. Given these facts of the world, I'm going to then ask you a question, and you sort it out for me. So there aren't really any fifth generation languages in common use. The only one I've ever actually worked with was Prolog, and that was in university days. And Prolog was fascinating concept, ridiculous for anything business related, because the idea was you would essentially say, here's a set of facts. Here is all the information that I know about the world. Here are the way that things tie together. Here are the inferences that you can draw from them. And now I'm going to write a logical statement, and I need to get the answer to that logical statement. It's a good demonstration for students. You provide them facts. You essentially build a rules engine. And Prolog did that. Now, it did it pretty slowly, and it was kind of difficult to work with. But, I could see certain scientific use cases where that type of language works out pretty well. So in practice, we don't really see too many true fifth generation programming languages. And so that generally is more of a research area as opposed to actual practice in business. And if you do want to learn a little bit more about programming languages, I do like this link that I've just dropped in chat, except that their explanation of fourth generation languages includes four languages that are not fourth generation. So Perl, PHP, Python, Ruby. Those are actually third generation languages. They are not fourth generation. They are still structured conditional programming languages intended to solve problems in that 3GL way. And also, mind you, when somebody says 3GL versus 4GL, it's not that, well, third generation, you shouldn't use it. It's not that at all. Vast majority of programming is going to be in a third generation language. It's actually kind of difficult to find good use cases for fourth generation languages. It's just we happened on one really, really good one. And it turns out that SQL is a really good language for this specific problem. So, given that fact, you don't see too many other languages. Now, if you go check out the list on Wikipedia, which I think is a reasonably fair list, as I was looking through it, the only one that I gave a little bit of side eye to was actually R and S as 4GL, which I guess I can see the idea, but I'm not sure I totally buy the notion of R as a fourth generation language. I kind of see it still as a third gen.
Yeah,
Nonetheless,
R is definitely third gen, Kevin. I mean, you have to tell it what to do. It has some things built in, but you certainly have a lot of working with it to make it do what you want it to do.
yeah, I guess it depends on how much you push the concepts of functional programming.
Uh-huh.
So, I would put most functional programming in the third generation in terms of capabilities, because I think it just fits there. But you could technically make an argument of extreme functional programming getting you closer to the fourth gen, where essentially you're again developing the descriptions of behaviors more than the implementations of actions, and leaving some other engine to run it underneath. So I don't know, there you could see some debate, but basically that's 3GL and 4GL in a nutshell. It's actually why SQL is such an interesting language. One reason why SQL is such an interesting language is because it conceptually is quite different from most common programming languages. Almost every programming language that people use is a third generation language. There are a few people who write in assembler, and obviously everything compiles down to machine code eventually. So, you do have those concepts that are available, but a tiny fraction of developers would use assembler as a primary language. They're going to use something like C. They're going to use something where that trade-off between specificity and efficiency versus being able to get stuff done in a reasonable fashion in terms of time, they're going to make those trade-offs. And generally, cut developer time tends to win out over cut bloat of software. That is essentially the trade-off we make, that I can write this app in an hour using some really high-level framework that's built on top of a bunch of other stuff that could do something that if you had to write it yourself from scratch in assembler would take you years. But at the same time, this is a 700 megabyte Electron app versus if you wrote it yourself, it might be 500K. So those are absurd exaggerations, but concepts there. So that was the tangent. Go ahead, Mike.
So interestingly, I mean, this is kind of rhetorical, but I have these weird thoughts sometimes where I hear about, like, okay, so you're in Python and you write f string, or you're putting a binary double, or you're using pyramid, or you're using like math.javascript, and you're using these things, and like, what happens when people who built them or who understand how it works are gone? Like, I feel like
good question, Mike.
There's so many things where you're kind of like, do people even know what this does? I mean, obviously there's security concerns. That'd be a whole nother tri-pass group probably, but like, I don't know. Sometimes I think, like, who knows how these things all work? And no one knows them all.
Right.
Yeah. This gets even bigger when you go into the Node world. So in Node, where just make a basic React site, a hello world in React Native, and you're bringing in hundreds of external packages, might even be a couple thousand at this point. For any non-trivial Node project, yeah, you've got thousands of projects or packages that you're bringing in, and that's just the norm. That is the way things are done. Where there is no standard library for Node, and therefore people have to create it. And so, you create these things and make them available, and other people implement them and inherit from them and build their own, and you all build on top of each other until the guy who developed LeftPad pulls it and breaks tens of thousands of projects.
Right. I downloaded reveal.js. I was learning how to do that, which is like based on the slides that you used to do.
Yep.
That tool that you used to demo, which I really liked. So I bought the course on Reveal, and yeah, I had to download what's the other one? Not Node, but Django maybe. I forget. But anyway, yeah, like I was cleaning up my computer, and there's like cajillion files for me downloading that package.
Yeah, Reveal.js itself isn't that crazy. It's a few JavaScript files. There's probably about a dozen or so if I remember right. But if you then put it on a web framework like Django, or if you were hosting it in Flask, if you were running it in any other platform, yeah, you're going to have all of those files that the platform brings. But going back to Aaron's post is a good one, and it is a good reminder that it's not necessarily how the query itself is written, it's how the database engine interprets it. What gets interesting though, is you could have two things that you as a human interpret as these should be the same, but the database engine may treat them differently. And welcome to performance tuning, where I just told you all this stuff shouldn't matter. Performance tuning is where we make money because it does matter. And the reason that it matters is that the database engine, if it had infinite time, infinite resources, could figure out the best possible way of getting data for any given query, any human written query that is syntactically consistent with SQL, that is of correct grammar. And if you gave it enough time, regardless of how poorly you wrote the thing, it could figure out that you intended this outcome. And there is one best outcome for that. The problem is that we don't live in a world of infinite resources and infinite time. We want that query to come back in, human time, not geological time. And therefore, we can't, except on extremely trivial operations, possibly parse all of the possible outcomes, check to see which one of them looks like it's going to be best, and execute on that. Or execute, really, if you want to get the best, you'd have to execute every single possible outcome, because even when you think something looks like it is the best, it turns out it may not actually be the best. Not exists versus left join versus not in. Yeah, you could write the same query, logically consistent result, by which I mean the results are exactly the same, using those three, and in that case, the database engine typically is going to make a change. Where, for example, not exists typically gives you a left anti-semi-join. And the reason it does that is because left anti-semi-joins are very efficient, but if you perform a left join, it doesn't necessarily know that a left anti-semi-join is a possibility in this regard. Therefore, it may not give you, it probably doesn't give you the same execution plan. Similarly, you can play with operations like apply. You could play with things like working with common table expressions, and even get more expressive, where by working with temp tables, you now technically alter the query, but the final outcome is the same. And that's where humans come in, where we can say that fourth generation language, the way that it translates into operations is not sufficient for our needs. I, as a human who has more domain knowledge than the database engine, may be able to improve upon that. Now, the database engine has a lot more inbuilt knowledge of logic, inbuilt knowledge of operations, and logic actually does make a pretty big difference. There are logical determinants based on the way you can write a query that could allow for filtering out of records. Who has more transistors? That's a good question. That's a good question, especially on Halloween. So you have this outcome where, as a human, I am able to affect the specific operations, thereby proving that the fourth generation language is not a pure fourth generation language, because a pure fourth gen, it doesn't matter how you ask the question, the outcome is always the same, and the process is always the same. In practice, you're not really going to get that. That's more of a hypothetical aspiration than a reality. So that was my what would I call that? Amateur hour version of computational philosophy. So on that, let's move to a less mind-bending discussion. And Mike, you've got some questions about indexes, and they're a lot less mind-bending, so we're good here. So Mike had a couple of questions.
It was a great discussion, Kevin. Lots to think about, so thank you. Just want to say mind-bending or not. What I got out of Aaron's post was that there is no one way to look at performance tuning, which is the way I was schooled when I started this career 20 years ago, is that when anytime anybody says performance tuning, I would think, this is to make the query run faster. This is, that's what I thought as a junior DBA, and it took me many, many years to understand that there is a lot more to it than just making queries run faster. So yeah. I saw a post that validated that. Yeah.
Oh yeah. Actually, you know what? Yeah. Since you jumped there, let's keep going there, because I think that's something that no matter how many times we talk about it, I think it's worth talking about one more time. And that is, code is written as much for humans as it is for machines. Yes, the machines run our code, but the machines don't care how ugly the code is. Humans care. And like I mentioned with that discussion of assembler, we optimize for human time much more than we optimize for machine runtime. There are extremes, like, hey, if this query is going to take 3 hours, but it'll be beautiful, and I can get it to half a second, but it'll be ugly. Yeah, if I need it to finish in half a second, I'm going to take the ugly query. But in most cases, like Aaron points out, the resulting code can be at least as well performing as an ugly version of it. And there's a lot of stuff to prettify code without losing any performance. Like, for example, you have concepts of indentation, of consistent alignment, of consistent spacing, consistent nomenclature, of using structures to make it easier for a human to read. So proper naming of attributes. Yeah, not naming your columns column 2, column 3, column 2b. Giving appropriate domain descriptions. Putting commas in the correct place. The correct place is after the column name and then a new line. And now we know why Mike dropped out, because Mike got banned. We now have a new opening for a board member at TriFact. No, keep losing audio. Yeah.
So I'm going to put the pause. Go on.
We put the ban button on
Hey,
Mike.
he disappeared.
Yeah, no, he had to. He's probably going to pop back in. He's losing audio. So we'll give him a moment while we're doing that. You know, it is a good idea to have human readable code, and part of human readability is consistency. Part of it is making reasonable decisions. Part of it is, like I said, spacing, indentation, making it so that code fits on a line. You don't constantly have to scroll back and forth. It's fairly easy to work with. And the easier you can make the code work with, given a set of performance, generally you're going to be in better shape. And of course, we can all argue about what exactly makes for something better than something else. I care less about that than I care about consistency in it. Yeah, commas after. Yeah, I mean, don't be a barbarian, Mike. We put our commas after our words.
They just made us do it here, so now I'm just like, now I do it all the time. I used to always do it your way, which is, I think the ANSI standard is to do it at the end.
It probably is.
I think it is.
But, okay, so now we got a couple of indexing related questions from Mike. First one was, you know, if I've got, say, no filters on a query, there's no where clause on a query, and there is an index column. So is there actually a performance difference? Like, for example, select employee ID from employees, or select employee address from employees. And let's say there's an index on employee ID. There's no index on employee address. Is this going to have any performance difference? The short answer is, what was it? No with an if. Long answer is yes with a but. So
I'm waiting to hear both.
Oh, okay. All right. Well, I was going to see if you wanted to jump in, Mala, but all right, I'll take it. So if you have no indexes.
No, I want to jump in, but I had a sense I may not be right. So go on.
Oh, you'll probably end up right. But let's say you have two columns. They're both ints. And I specify data type here because that will make a difference. And I'm going to talk about SQL Server specifically because if we're talking Oracle, behaviors may be a little different. I couldn't tell you for sure. But SQL Server, you pack data into 8 kilobyte pages, roughly 8 kilobytes, is slightly less, but let's not talk about that. Just make it simple. Let's make it incredibly simple. An int is 4 bytes, a page is 8K. So that means you can fit 2,000 ints on a page. All right, I don't want to hear anything else. Pi is exactly 3. That's what I'm getting at here. And so you can fit 2,000 of these ints on a single page. Now, I have no where clause. I want to get every single int from every single page. If I have an index, I can pack 2,000 of them on a page. If I do not have an index, specifically, if I do not have a non-clustered index specifically tailored to that one column, then if I have let's say I have a clustered index, but it's not on the column I'm searching for. Well, the clustered index, where the data lives, very simplified version of this, we have 2 columns, 2 ints. That's all I specified, 2 ints. I can fit 2 ints together. That's 8 bytes. And we remember we have 8K, which is exactly 8,000 bytes. I don't want to hear any guff. So we can fit exactly 1,000 pairs of integers on a page. And because we believe in normalization here, we believe in first normal form. There's no such thing as null. You have those 2 ints. So you have 1,000 on a given page of 8 kilobytes. So if I have X number of records, I am going to get it in X over 2,000 reads, basically a scan that hits X over 2,000 number of pages of 8 kilobyte pages. If I have an index, it's going to be X over 1,000 if I have no index. So basically, it will take 1/2 of the number of reads to scan through that whole list if I have an index on that column. It doesn't matter if I have no filter specificity. The fact that I can narrow down to just a structure that includes that record and that record alone was sufficient. And by not being able to, I now have to scan through a larger data structure that takes more pages, that will take more memory. -1 is used as a stand-in as null for null. Sentinel values are weird, and I don't like them. Have a value. Make a stand. Make a determination that you're going to have a value. We all have value. We should have values in our database. Vote Kevin 2024. So that's the simplest possible version. Coalesce. So if you don't have a value in there, you're just going to return null. Actually,
Yes.
You're just going to get -1. It's always going to be -1. But I like the idea of coalescing this or null. It's like, why not just have that thing? But the simplest answer, if you have an index that is smaller than the total size of the data, then you will likely get at least some minor performance benefit from specifying it versus the entire clustered index or the entire heap.
So, can you remind me the clustered index versus non-clustered? One of them's an actual physical object.
Well, they're both
Right.
physical objects. The idea of the clustered index is essentially our definition of this is the structure which holds the data for our table. The non-clustered index is a physical structure which represents some subset of columns that are written and kept in line with the clustered index.
Okay, so that's the idea. Okay, so like the imp ID, if that were in a non-clustered index, it would be stored. It has a physical page where all of them are on exist.
Yeah.
Well,
Yeah.
I mean, there are multiple, more than one page because pages are kind of small, but depending on how big the table is, obviously. But
Yep, it is written out to disk. It is handled in that way similarly to the clustered index. And also, in an example like this, you could have a non-clustered index on maybe has 2 or 3 columns, and your imp ID is actually the third column. That's still okay because you're scanning the entire index anyhow. So this would suck if you had a where clause where you filtered, but if you're literally don't care, scan whole thing, then technically the best performance is going to be give me the structure that has the fewest number of things that I don't care about, and it has all of the things that I do care about. Where things
That's
get
a
really
great way
tricky.
to put it, Kevin.
And
Things that. Say that once more, please.
sure, if I can remember it. So in this scenario, because you're essentially saying scan the whole thing. I don't have any filters. All we care about is ensuring that we have the fewest things on there. All of the things we do care about and none of the things we don't care about. And things here, I mean columns. So if I need to return back 3 columns, that index, if it has all 3 columns, is the most efficient path for accessing all of the data. This is a rare case, mind you. As soon as you introduce the idea of any kind of filter, now we have to start talking about actual strategy. This is I'm playing Boggle versus chess. I'm just like smacking the thing and seeing what comes up. Just give me all the letters versus actually thinking through, actually planning through and strategizing. This is the simplistic answer. But given that question where it's always going to be a full scan. In that case, the only thing you really can do is narrow down as much as possible what you're scanning in terms of number of columns. If you have a column that you want to include in the scan, so like your example is selecting employee ID from employees. Well, if you say, I have an index on employee ID, great, you've done the job. But as soon as somebody says, I want to select employee ID, comma, birth date, that index no longer helps. And what ends up happening is, in SQL Server, one of two things. One, you scan the clustered index. You ignore the non-clustered index. So you go back to, this is the worst performance of a scan. Or, I put scare quotes around worst because this is probably going to be way worse, which is you read the records from the non-clustered index, and for each record you do a key lookup back to the clustered index to seek. So if you have, where this matters, if you have millions of rows, tens of millions of rows, instead of one scan of a table that is tens of millions of rows long, you have tens of millions of seeks. And each seek, by the way, is probably going to be about 3-4 page reads. If you're talking tens of millions, you're guaranteed 3. You're probably guaranteed 4. Once you have more than like one int on the page. And depending on how many tens I mentioned in tens, let's say 30 million, you're guaranteed 4 pages minimum. So, or four pages per seek minimum. So 30 million, 4 pages, that's 120 million reads, 120 million IO operations. For reading those 10 million rows as a single scan might be 50,000. That's an enormous difference in IO, brought about by not using an improper index. So that's why I say you have to include all of the columns, and to maximize the performance of that, you only include the columns that are in your select clause, which means if your select clause ever changes, that index would need to change. And hopefully nothing else uses that index if you want to change it. So yeah, very long-winded way of saying that, yes, it does matter. Now, here's where I come back and say, does it matter? Because if you're talking tens of thousands of rows in a table, who cares? If you're running on anything faster than a Raspberry Pi, you probably can't even tell the difference between a scan of an index and a scan of a non-clustered index and a scan of the clustered index. You probably can't tell the difference. It's literally microseconds. So unless you're looking at incredible throughput, you've got hundreds of thousands of these scans every minute. In which case I might say, holy goodness, what are you doing? Don't do that. This sounds really bad. There's got to be some better way to do this. Hypothetically, if you're doing that, then yeah, now this probably makes a difference. But for most corporate cases, we run this query once an hour. It scans 10,000 rows. I can't make it scan fewer than 10,000 rows. For whatever business reason, it has to scan the whole table. I wouldn't bother with an index on that. Even if you get some performance benefit, you're still doing a full scan of the table, and also any updates that happen, you do pay the price of updating the non-clustered index as well.
Can I give you a hypothetical?
Sure.
So I'm just trying to demonstrate something at work. It was one of the reasons that this came up is like, I want to do some quick wins for some of my colleagues, like search arguments and order by and some things like that. And so I have a index with 3 columns. It's like patient ID, patient name, and birth date. And if I select those 3 columns from the table, it is a lot. I mean, it's 6 million records, let's say, ish. 11 seconds. If I only select like 2 out of those 3 indexes, and I get that if I add something that's not in there, now I'm getting into the description that you just said, which was if it's not part of the select, then it's got to do all the extra work.
Mhm.
But what if I only take 2 out of the 3? Is that if I had like patient ID and patient name, but not birth date?
Again, predicated on there is no predicate, there is no where clause.
No,
No big
nowhere
deal.
close, right?
Yeah,
Okay.
technically could be more efficient if you removed the column from the index. In practice, I wouldn't bother,
Right.
especially if there is volatility, if there's a likelihood that somebody would want it again. So if
Uh-huh.
99% of the time they want the 2 columns and 1% of the time they want the third column, might as well just give them the third column in that case.
Okay, so does the order in which you create the index columns matter?
In a non-degenerate scenario, yes. In this scenario, which I'm labeling as degenerate, no, not really. Because you're not seeking, you're not looking for an individual record. You're literally give me all of the records. And because you're saying give me all of the records, the only thing the optimizer can do is scan that whole thing. Which means it doesn't matter if the order is int string date or date int string or whatever. It needs to give you back all of them. So
Mhm.
where it does matter is as soon as that where clause kicks in. Now, if all of the queries are on date, the patient's birth date,
Yeah, for 1945 and later, I did something like that. Yeah.
then having birth date be first may be a possible good solution. If most of the queries are based on patient ID instead of like if everything's got patient ID, patient ID first, usually a good solution. So essentially, at that point, now we start talking about I have selectivity and I want to get my most selective things first. The things that are
Okay.
or the things that are most selective in the most scenarios. So if almost all of my queries have date of birth, and every once in a while I have a patient ID as well, then I'd put date of birth first, even though patient ID is more selective, probably. Well, almost definitely.
Yeah, certainly patient ID is
I mean,
numero uno.
I guess it depends on how many patients you have. Then you'll
Yeah,
have a
like
birthday
6
problem
million.
eventually where 2 of them share the same birth date. Now patient ID is
Oh,
more
and
selective.
twins. We have all kinds of. We have twins, triplets. They have very
Oh yeah,
similar.
yeah. I
Yeah,
mean,
we have
when you're
all kinds.
talking millions of people, yeah. Patient ID is going to be more selective. But
Yeah.
if it turns out that you rarely query by patient ID itself, like you need to find the patient ID based on the date of birth and the name, well, in that case, I wouldn't include the patient ID first because that's not your filter. That's not where your query is selective.
Yeah, we probably filter most on birthday, but yeah, you're right. We don't filter on individual patient IDs really ever because it's like PHI. You don't want to be putting it in your code. We usually create cohorts based on did you have this disease or that disease.
Yeah, so that's where indexing like where it becomes strategic as opposed to uh, barbarian with 4 intelligence. Intelligence
Okay,
is
and
a
then
dump stat.
well, intelligence is a dump stat for a berserker level 5 something or other. So I'll probably ask more. So as I'm transitioning from Oracle to SQL Server, we're using SQL Server more. Like we also have everything like hidden behind views. So I'm also like, even though I'm trying to learn more about performance, like sometimes I have extra challenges of you can't even really query the underlying tables, which is smart because for a variety of reasons. But at the same time, I know some of the performance stuff is not as straightforward when you're using views.
So a question comes in from Enhanced QC. Wouldn't you tokenize or salt your PII or PHI and reference that in your code? And that is a really good question. The short version is depending on how you define tokenize. So if you're talking one-way hash, probably not. except for stuff that you never need to translate back. So that may be something like, in practice, that'd be something like a credit card number, perhaps, if you're the payment processor. It would be something like a password. It would be something where I need to know that you know it. I don't need to know what it is, but I need to know that you know it and that I have a method that translates what you know into this end result that I can use.
Yeah.
If we're talking two-way encryption, where I might encrypt a patient's name, possibly, and in that case, that would be a scenario where I want to have some other system that is doing the decryption, but when storing protected data, I guess it depends on if you're using the protected data as part of your key filters. So like if you have, say, range filters on people whose last name is like something, performance can get really bad if you are encrypting all of the data, because that like operation becomes really difficult to do in a translation when you're using any sort of encryption service, and that includes always encrypted in SQL Server.
So that's a good question. We have used for some. So it depends. So if we have projects, it depends on the IRB. If we have projects with outside entities, we definitely, like recently we did something called an HMAC. HMAC.
Yep.
We created a function based on the HMAC standards, and generally speaking, we always have to be able to figure out who it is. So, Kevin, you have to somebody has to be able to re-identify. So, per your comment earlier, and then generally speaking, very select people like myself we can see PHI, but we have all kinds of restrictions in place, and we don't ever share it. And depending on the type of study, like if you have a consented study where someone signs a consent form saying that we're going to use your information, even when we get permission to use it, we only use it if we absolutely have to. So like I don't think I've seen patients' names, and like I can see patients' names, like I just brought it up in my example, but I never bring it into queries. Like just never do it, because why would I? Unless I'm troubleshooting something. So yeah, we try to be really careful with it, but we don't usually do de-identification unless the IRB calls for it. And we're also not sharing any PHI and any operational type data, where like how many people came into the emergency room. It's like a chart. It doesn't have anybody's information.
Yep.
I'm sorry. IRB, Internal Review Board. It's the academic process for approving studies and research. Institutional Review Board. It's at every place that gets government funding for research has to have a board in place per FDA guidelines.
And when Mike was talking about an HMAC, that's a one-way hash. So think of like SHA 256, SHA 512, Md5. Those are examples of HMAC hashes, which means that's an easy case of I have some piece of information. I know that I can get to that point, but I don't have a way of getting back from that point. So you can give the, say, SHA 2512 output, or SHA 3512, either one. 2 and 3 are both supported there. But you could have that output. You could give that to a third party. That third party is not going to be able to determine from that what the person's name was, because they don't need to know the name. They just need to know this identifier represents a unique person. And whenever you see this thing, it represents the same unique person. You don't need to know any of the details about that person except what is relevant for whatever study. So that may be, say, diagnostic codes. That may be hospital visits, inpatient, outpatient. It may be the nature of the visit, what the follow-up regimen of treatment was, and what the outcomes were. That kind of stuff a third party might be able to do without knowing that this is actually Bob Smith who lives over here. And so in those cases, yeah, you would definitely want to have that data be as well protected as possible. But when it comes to, let's say, by contrast, we're talking about nurses who need to be able to look up the names of patients. Nurses, again, this is probably when you're looking up name, they typically have to do a full match. And in that case, you can encrypt the names underneath without any real performance hit. It's where you have to do partial matches when things get really tricky. So as long as your input validation removes or doesn't allow for spaces, etc. Yeah. I mean, you can. So you could, if you're talking about the input message can have whatever character, whatever shape you want. So your input message could be an entire book chapter, and it gets turned into this digest, this hexadecimal string of output that represents whatever input you gave it, which leads to the possibility of collisions. So it is possible that two people have exactly the same hash result. It's extremely unlikely as you get to like SHA 512, which is why I brought that up as an example, but theoretically possible. And how HMAC one-ways look like. With different character-based languages. Okay. Yeah, that's... to get that, I would actually recommend looking up the Md5 standard. It is certainly an old standard. It is not used at all for most use cases anymore. By which I mean, you'll still see it for things like, I want to prove that this piece of software hasn't been tampered with. But yeah, it is used in courts, yes. That's because it's old. I say that only half in jest, but it is still useful in certain respects, understanding that it is not useful for security in the sense of, I have given you an MD5 hash, there's no way that you could reverse it. Because it turns out MD5 was actually pretty easy to reverse in terms of rainbow tables. But I would recommend looking at the standard for that. Look at the process for it. Actually, Ross Anderson, if you're really interested in all of this, I need to grab a book.
Oh boy.
Yeah, this is a big boy. This is definitely a big boy. Ross Anderson wrote literally the textbook on security engineering. And in this book,
oh my goodness,
there's probably like 5 or 6 chapters on exactly how cryptography works in practice. And he starts, it goes everything from the really simplistic understanding of it to very deep understanding of implementation. And he covers a lot of other stuff in the book as well. So very highly recommended. I bought this copy more than a decade ago. Given that it's a textbook used in universities, I would expect it'll be in like the 7th edition by now so that they can maximize the money. But grab a copy of that if you want to really dive into cryptography. Understand this is a rabbit hole. This is a place you may not drag yourself out of. If you start going down that rabbit hole, it may be a while. So that is Security Engineering by Ross Anderson.
I don't know why my camera keeps cutting off.
Oh, your camera's still on, Mike. We can see you. Mike can't hear us anymore.
uh-oh.
There we go. And
I don't know why that keeps happening.
oh, Mike's second question. If an index has multiple columns, How do you make best use of the index in terms of writing a query? Ross Anderson.
Who's that?
He's the
He is
writer
a-
of security engineering.
Yeah, he's a professor, I think, at
Oh,
Cambridge.
okay. I was like, when Kevin mentioned an indexing question and then said something about some
Oh.
Anderson, I was like, I've not heard of anybody like that.
Yep. So, all right. How do you handle indexing in terms of multiple columns? Like I mentioned, selectivity is selectivity of your queries. What are the things that narrow down the most rows the fastest and give you back the fewest resulting results? So look for the things
Did
that...
you mention filtered indexes, Kevin?
I did not mention filtered indexes. So I'm the security engineer that occasionally
I love
pops in here.
filtered
Excellent.
indexes.
Excellent. So yeah, so that book might be right up your alley if you want to dive into cryptography. It is like I said, it is a textbook that he uses when he teaches courses. So definitely worthwhile, and is kind of the lead into some of the PhD level cryptography. He doesn't do any of that, but he leads into it. And sorry, Mala, I cut you off there.
No, you don't mind. I can keep track. Don't worry. You were answering this person. I understood that.
Okay. So yeah, look for selectivity, and for filtered indexes, Mala does mention those. That'd probably be a topic for another day because they're interesting. I wish they were more useful.
And useful.
I wish they were more useful.
Oh, you think they're not useful? Oh, okay.
They are useful. So if
Maybe.
you can make use of them, they are incredible. However, the restrictions that you have on what the database engine needs to know before it can make use of it makes it so that it is really difficult to use them in practice. So
Fair enough. But let's have it for another day discussion.
Yep, because we are at the top of the hour. So with that, everybody, remember that tomorrow, no meeting. Our first meeting of the month is next Tuesday, the 14th. And we've got 3 outstanding people lined up to talk about topics of very good interest. And with that, 3rd edition is on the way. Okay, wow. I'm actually surprised that they haven't already milked 3 editions out of him since then. But check out the 3rd edition of Security Engineering. And with that, we're going to say, everybody, until we see each other again, take care.